Okay. Thank you. And I'm not even sure that, the last class Zoom session didn't actually turn up in my, I didn't get a, I don't know if Zoom actually recorded it because I didn't get a message about it. Anyways, I'm going to pick up exactly where we left off. And today's a bit of fun, right? So here's where we were in the last class. Aha, Zihaw's here too. Hi, Zihaw. So we saw what a uh, Hopfield net was. So let me start by reminding you what a Hopfield net was. And in fact, why don't you remind me? So Kinari, your turn. What was a Hopfield net?
Hopfield net was a fully connected set of neurons where the input was some additive constant to it to a affine combination, and
So it
then
was
each of the
full.
networks pass an input to each other, and as a
Right. So
result, they would iteratively start to approach some
yeah.
minimum energy.
So you had this kind of network where each for each network neuron you had Zi j not equal to I Wij. We assume that these weights were symmetric, right? Times Yj plus maybe Bj, and then we said Yi equals the threshold activation of Zi, and we found that Yi flips its sign if Zi was less than 0. So this was the basic model that we had. And we found that this was some kind of a memory. What did we call what kind of memory did we call it? Jamba, please.
Content-based memory.
Content addressable memory, correct?
Right.
And the question was, okay, how do we make the network store a specific pattern or set of patterns? And basically, how do you teach the network to remember maybe this pattern, right? And the example we saw was that the way what we wanted to do was to choose designing the network was the same as designing these weights, and you had to set these weights such that for the pattern that you're trying to store, this energy is a local minimum. If the energy is a local minimum, then if you set the network in that pattern, it's not going to change from there. And if you move it a little bit, it's going to come back. So first thing, we wanted the pattern to be stationary, which meant that the sign of the affine function at each neuron had to be the same as the sign of the target pattern itself, right? The target bit. So if this happened, then the bits would not flip. So this was stationary. And then you wanted it to, and we found that if I just say, if I have a network, so suppose I have, for example, a 4-bit pattern that I want to store, and I just say want to store -1, 1, 1, -1, this kind, then we could use Hebbian learning to compute the weights. So in this example, what would this weight be according to what we had done in the last class? Anybody remember?
-1.
This would be -1, and why so?
Well, the multiplication of both of these.
Yeah, exactly. So this was -1, this was going to be 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 1, this was going to be 1. So basically we said Wij equals Yi times Yj. If you did this, then this was Hebbian learning, correct? And we saw that when you use Hebbian learning to learn the weights, then first thing you find that it is stable, it's stationary, because if I just look at the sign of the affine function at every node, it's going to be sign summation j not equal to wji yj. I'm ignoring the bias term here. And wji is simply yj yi. If you work it out, you get yj squared, which is just +1. So yi comes out because the summation is not over I. You are left with, and so it's yi times a positive constant. So the sign of this thing is the same as sign of yi, which is yi. So as a result, what we found was that if we used Hebbian learning, the pattern was stable, it was stationary. We also found that when you work it out over the entire network, the total energy of the network ends up being a global minimum. And so as a result, the pattern is also stable. And then we saw an example over here. This is a 4-bit pattern. I'm representing the 4 bits as a Carnot map. If I want to store this bit pattern, which is 1, -1, 1, 1, all of you remember Carnot maps, right? Shams?
Yeah.
Yeah, right. And you guys. So if I want to store this bit pattern, then and I use the Hebbian learning rule, you get this energy for the various configurations, and you find that the energy is a global minimum at the target pattern and at its reflection. And we saw that for any pattern, the reflection must also be a stable pattern because the energy is a quadratic. So if y is stable, minus y is also stable. That's about it. Now, where we left off is, okay, we see how we can store one pattern. But suppose I want to have the same, remember, this is a memory, right? You don't want to use n bits to store only one value. You want to store many different values. So what if I want to store more than one pattern in my network? Well, if you want to follow the Hebbian learning rule, what you can do is to simply average the weights that you would get for all of the patterns that you want to store. So for example, if I wanted to store, say, this guy, 1, 1, -1, -1, then this is going to give me, say, -1, -1. Let me add this with a different number. -1, -1, -1, -1, 1, and 1. So these would be the weights that I would need to store this pattern, right? But at the same time, suppose I also wanted to store a different pattern of this kind, which is, say, 1, 1, -1, -1. So for 1, 1, -1, -1, the weights are going to be 1, -1, 1, -1, -1, and -1, right? So if I want the same network to store both patterns, one obvious choice is to take these weights and these weights and average the two. So this is the simple Hebbian learning rule. And come on, okay. And if you use the Hebbian learning rule to do so, what would be the problem in trying to average the weights in this manner? Does anybody want to guess? Jean-Baptiste?
There'll be 0 if you
You
have.
get 0, but 0 is not necessarily a problem, right? The problem is that the weights that are good for one pattern may not be good for the other pattern, right?
Oh yeah.
So it's going to go into bad places. So given that you can have clashes of this kind, how many patterns what is the largest number of patterns you can store? And what John Hopfield did was he worked out the math for it, and he said if you're trying to store random patterns, right, not structured patterns, but if you're trying to store random bit sequences in your network, then you can store up to 0.15 n patterns using Hebbian learning. So if here, for example, n is 5, this network has 5 neurons. So you can store 0.15 n, which is basically you should only be able to store one pattern in this particular network. This network doesn't have the capacity to store more than one pattern. As you increase the number of bits, you can store more and more patterns, but the upper limit is 0.15 n. Where did this 0.15 n number come from? He worked out the arithmetic, right? And it turns out, I'll skip all of the arithmetic over here, but remember, it goes back to this figure over here. This is the set of weights I want to store this pattern. This guy is the set of weights I want to store this pattern. When I average these two weights, these weight values will end up interfering with my ability to recall this pattern, right? So this one here, this one interferes with this guy, and this guy interferes with this guy, right? So you're going to get you're going to get interference. And it turns out that if you work out the math, you say, so there's a very specific criteria. Now, basically, we want for any pattern, remember, this 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 behavior is required, right? You want the product of the bit at any value, any location, and the field at that location to be positive. If you're using Hebbian learning, then you're guaranteed that if you're storing only one pattern, this will be positive. But then you get the contributions of the averages of the other patterns, and these guys can drive the total energy to become negative. You can work out the probability. What is the probability that this total energy is going to become negative? It won't work through the math. But if you assume all of the patterns are random, then you basically end up with this little probability which says that there's a probability of if you try to store less than 0.14 n patterns, then there's a probability of less than 0.4% that some of these patterns are not going to be stored. So this is not a great value. Think about this. If you're trying to store 1,000 patterns in your memory and 4 of them get damaged, then that's really not a very good value. But it turns out that if you work through the arithmetic using Hebbian learning, if you think that getting 4 out of the 1,000 memory patterns damaged is acceptable, then you can store a maximum of 0.14 or rounding up 0.15 n patterns in a memory, which is not great, right? So this is let's actually try to use Hebbian learning and see what really happens. Try to visualize things. Here, I am trying to store just one pattern. I use Hebbian learning. You can see that that one pattern actually ends up being at the global minimum. This is the pattern I'm trying to store. This is the energy contour for each of the bit patterns. And you can see that the energy contour is minimum at the pattern I'm trying to store and also at its mirror image. At the other locations, the energy is higher. So if you started off the network, say at this point, this is the highest energy. So it's going to evolve into this place, which has a lower energy. And from here, it's going to evolve into this location, which is lower energy still. So regardless of where you start, if you start here, it's probably going to go here and then go here, or maybe just wander down like so, go here and end up here, right? So if you try to store only one pattern, you can set these things to be the global minimum. But if you try to store two patterns, here's what happens. This is the energy contour. You find that both of the patterns end up being stable because they're global minima. But you have a 50-50 probability of being able to recall a pattern. For example, if you just flip one bit, and if I set that and my erroneous initial pattern is this blue location, then it has a 50%, and then it can either evolve here and go here, or evolve here and go here with equal probability. There's no guarantee about which pattern it's actually going to recall. But if you start off in the correct locations, so these are the two patterns I'm trying to remember, these two guys, and these two are their mirror images, they're ghosts. Those patterns are stable. If I try to store there's something very interesting over here. These two patterns are maximally distant. These two patterns have less than maximal distance. They end up being more stationary. But let's keep the fine detail, right? I have several examples of these for 4-bit patterns. The interesting thing that happens is that when I try to store 4 4-bit patterns in a 4-bit network, this is the energy contour. What is this energy contour telling me? These 4 stationary patterns, these 4 patterns are stable. If I start off in any of these 4 patterns, they're not going to move. But every other pattern is stable. There's no pattern that's not stable. So it doesn't matter where you start the thing, it's going to stay right there, right? So it's not really remembering things properly. Or let me say something else. Let's look at this guy here, right? This is not a good one. These are 6-bit patterns. So I'm drawing a 6-bit Karnaugh map. And you can see that if I try to store one pattern, I'm able to store it. If I'm trying to store two patterns, these end up becoming kind of local minima again. If I want to store more than two patterns, then you get some very strange behaviors. And the strange behaviors are these. Consider, say, does it show up over here? It's not really showing up. I'll like this one, right? So consider this square over here. This square is not a pattern that I'm trying to remember, okay? But if I start off the network at this location, if I initialize the network to this location, it's going to go here, and all of the neighboring locations, so locations neighboring this guy, have higher or the same energy. So in other words, the network is going to wander into this location and stay there. It's not going to move away. So this is a fake memory. Here are the four memories the network is trying to remember. This guy ends up being a fake memory, a location where the network can simply wander into that location and stay there, and for all practical purposes, it's going to pretend as if it's a valid memory. Or here is this other guy. This guy too is a stable, if you look at this one, this guy is a fake memory. It's not something that you really want the network to remember, but in the process of trying to make these patterns memorable, this pattern becomes stable as well. It's not actually going to, the network is remembering things that it was never really intended to remember things that didn't happen. And this happens in for humans, right? You get these interpolated memories, which you try to recall something from your fourth grade. You don't know if that person was left the class in the fourth grade or not. You're going to begin munging up things as you go further into the past. So these are basically confusing, almost real memories, but they're not really genuine memories. They're fake memories. And these are, as you keep increasing the number of patterns you want to store, you end up with these fake memories, which are stable and sometimes stationary and sometimes stable patterns, which are not patterns that you want to remember. And so I won't actually bore you with the details of these examples, but what actually comes across is this. Two things happen. First, it's possible to get more than 0.14 n stationary patterns, but this always comes at the cost of these ghost memories, fake memories, which are things that you don't want to remember, that the network ends up remembering. So this was where things were when Hopfield first proposed this network, that Hopfield's learning mechanism, which was Hebbian learning, could potentially store up to 0.14 n patterns, but this always came at the cost of all of these fraudulent memories, things that the network was not supposed to remember, and it did. So at the same time, under different settings, they also found that Hopfield and others also found that it can in fact have more than 0.14 n stable memories, just that it comes at the cost of these fraud memories. So, and there's another thing that they found. Suppose I'm trying to store 8 memory patterns in an 8-bit network. Then if I were trying to store these 8 patterns, here is the energy contour that I get. Every pattern ends up being stable. So it's not just the memories that you're trying to remember, but the other guys also end up becoming stable, meaning the memory becomes non-discriminative. It's not recalling anything. It likes anything that you initialize it with, right? So it's no longer a content addressable memory. It's like, okay, you give me something and I'll store it. It's not really a very useful thing. So the bottom line is something like this. The networks apparently have a capacity to store more than 0.14 n patterns, but it comes at the cost of many parasitic patterns, undesired patterns that also become stable or attractors, right? So why do we get these fake memory patterns? The fake memory patterns are because of this. If you draw an energy contour of this kind, you are designing the network to have these energy wells. which is which are the memories that you want the network to remember. But in the process of designing, you end up with these little, unplanned wells in the energy, and these become your parasitical or spurious memories. And this is an issue, right? It's remembering things it doesn't want to remember, and very often these guys don't actually end up being in wells. So let's sort of continue with. So here's where we stand, right? When we use the Hebbian learning rule, this was the Hebbian learning rule. It's a very simple idea. But in spite of its simplicity, it's kind of complicated in that the behavior is kind of not predictable as far as we can make out. And if you want to store more than one pattern, it may not really work. Okay. So we're going to do two things in the rest of the hour. First, we're going to spend 10 minutes figuring out why this didn't work. And second, we're going to see how we can fix it. Okay. So let's look at why this didn't work. First, I had Wij equals Yi Yj, right? That's how I computed the weight. Suppose I put my weights in one pattern, right? So this is my first pattern. This is my first bit. This is my, let me call this the nth bit. Then my weight matrix, W, really is, the diagonals are all 0 because there is no self-connection in my networks, right? The off-diagonal terms are Yi, Yj. So this weight matrix is simply Y times Y transpose for all of the off-diagonal elements. But the diagonal elements are being sent to 0. But what are the diagonal elements of Y times Y transpose? They're just 1. So the weight matrix becomes Y times Y transpose minus I. So when I simply use Hebbian learning, my weight matrix becomes Y times Y transpose minus I. Very simple, okay? And this explains the behavior. When I'm trying to store multiple patterns and when I'm trying to average or sum all of these, the Hebbian weight matrices for the individual patterns, here's what I'm doing. I'm summing over all of the patterns that I want to remember, Y times Y transpose minus I, right? So this is the weight matrix that I'm trying to remember. Now, if let's say I have two patterns, 1, 1, minus 1, minus 1, and minus 1, 1, minus 1, minus 1. I can put both of these patterns into a single matrix, and the weight matrix equation simply becomes Y times Y transpose minus 2I, okay? Because the weight matrix for the first guy is Y1, Y1 transpose minus I. That's what I get from this one. For the second one, I get Y2, Y2 transpose minus I, which is what I get from this one. And when I sum these two, this just ends up being this matrix equation, okay? So I can just write the matrix equation in this manner. That's Y times Y transpose minus Ni. And if I just work through this whole process first, let's try to analyze the weights matrix. One of the properties of any matrix when you're doing eigenanalysis, if you say, does anybody remember the eigenvalue equations? Hinori, if I have a matrix, what is the eigenvalue equation?
So it's W times the eigenvector equal to eigenvalue times the eigenvector.
Right, so this is what we want, correct? And observe that if I suit W minus I, where I is an identity matrix, V equals lambda V minus IV, correct? Which is the same as saying lambda minus 1 times V. So when I subtract an identity matrix from a W, it doesn't change the eigenvectors. It only changes the eigenvalues. And so based on that, we can analyze this model, right? The behavior of YY transpose minus NP times I is identical to the behavior of YY transpose. So if I look at the energy for any particular Y, any particular pattern, then it's going to be the weight matrix Y transpose the weight matrix Y, which is Y transpose Y transpose Y minus this additional term, which is just a constant. So subtracting this diagonal matrix, making the diagonal matrix, diagonal values of the entry matrix 0, basically just shifts the energy contour up and down by this little constant, okay? So that means I can just focus on analyzing just this YY transpose, because subtracting a diagonal matrix doesn't change the eigenvectors. And this guy here is a positive semi-definite matrix. So now let's look at the energy function again, right? The energy function was minus half Y transpose WY minus B transpose Y. What sort of an equation is this? Is this a
It's a quadratic equation.
it's a quadratic, right? How many maxima or minima will it have?
1.
So how are we saying that, you know, so whereas I kept drawing these figures and I kept showing multiple minima, right? So how can we match what we have over here with the fact that this is a quadratic? Anyone?
What do we mean by matching?
So the quadratic has only one peak, right?
Yeah.
Whereas when I was talking about it, I say you have multiple memories because there are multiple minima in the energy contour.
Yeah.
Right? Whereas this guy is the energy, and this clearly has only one critical point. Right? So I'm making two seemingly contradictory statements. On the one hand, I'm saying that the energy contour has multiple minima, and on the other hand, I'm showing you a quadratic energy contour, right? And energy is a quadratic.
Right.
So we know that W is positive semi-definite, so the energy is concave, meaning it has a peak. So what really happens is that the energy looks like this. Let's say bowl bending downwards, okay? If I look at it from the top, and if I take slices of the energy, then the energies, equal energy contours, it's going to be maximum out here in the center. And as you go away, the value is going to keep coming down. But then we have a binary network. The binary network can only take these values, minus 1, 0, 1, 1, 1, 1 minus 1, and minus 1 minus 1, right? So this means that this is a peak. Now, the closer this ellipse is to the center, the higher the value, right? So how many minima? So these are the only 4 values that the network can take, the 4 yellow dots. So how many minima does this one have? Can you tell me by looking at this figure?
Within this space 4.
Yeah. So remember, the network is binary, right? So it can only take one of these 4 yellow values. And so these two guys are further away from the center than these two guys are, as you can see, based on the ellipses. So these two are minima, these two are not minima, these two are going to be the stored patterns. Making sense, guys?
It's both.
I have a quick question. I got confused. So we said that the energy had like multiple local minimas.
Yeah.
Did we just say it because we had some parasitic memories that we said, okay, these things interfere and we don't remember things clearly?
No, it's because you could be trying to store it's in addition to the parasitic memories. If you're trying to store multiple patterns, then each of those must ideally be a local minimum, right?
Yeah.
That's why.
Oh, okay.
Right? And so what happens is that the big patterns, Y can be only one of these 4 yellow values because it's all binary, okay? And those binary values so the only values that configurations that the network can take is one of these 4 yellow guys. The closer the yellow guys is to the center of the energy contour, the higher the energy at that pattern. So the ellipses which are further away from the center, they have lower energy, so these two are going to be the patterns that the network remembers. Those are the stored patterns, okay? And if I go into 3 dimensions, this is where I'm remembering a 2-dimensional pattern. If I'm going to start having 3 dimensions, I have a 3-dimensional higher cube, and the network can be only in one of these 8 corners. If you ask it to store 2 memories, then it's going to be these 2 guys, and then you're going to have, and you can see why, because of symmetry, this fellow is going to be at the same level as this guy, right? So every pattern and its negation are going to have the same energy. So you'd have these 2 guys who are the stored patterns and their negations, and so on, right? Now, let's look at what happens when let's look at a 2-dimensional network. A 2-dimensional network means that you can only store these 4 patterns, correct? And the evolution of my network in vector is going to be y equals sine of w times y. W times y is the field. You're taking the sine. And so this is the actual evolution of the network written in vector form, okay? Now, if I'm trying to store this pattern, what will w times y do? Anytime you take a vector and you multiply it by w, that is going to maybe rotate the vector and increase the length, right? This w times y is going to take the vector and put it over here. And then when you take a sine, this guy is going to snap back to the closest corner. So what this means is that at each evolution step, this w times y is going to sort of rotate and scale the vector, and then this sine is going to snap it back to the same corner. And so long as w times y keeps the vector within the same orthent, this operation is going to keep bringing the vector back to itself, right? So if your weights matrix is such that for all of your desired target patterns, w times y keeps the rotation within the same orthent, then the pattern is going to be stable, okay? So basically, every time you start off with a pattern and you do a w times y, it's going to go to a new location. You take the sine, it's going to snap it back to the closest corner. And so long as this rotation keeps it within the orthent, that pattern is stable. Now, so stored pattern is stored if sine of wy equals y for those patterns. So we want to design the w such that this holds. What is the simplest way of making sure that when you multiply a vector by the matrix and then you snap it to the closest corner, it comes back to the original vector? The simplest way is if wy equals lambda y, right? Where lambda is a positive term. In that case, multiplying by w is simply going to lengthen it, and then doing the sine is going to bring it right back to the corner. So if the patterns that you're trying to remember are eigenvectors of your weights matrix, then that pattern is guaranteed to be stable, right? And how many such eigenvectors can we have for a matrix of, n cross for an n-bit network? The matrix is an n cross n matrix, and n cross n matrix is going to, and furthermore, the matrix is symmetric, the way we defined it for the Hopfield network. And now in an n dimensional space, you can have at most n orthogonal vectors, number one. And number two, for any symmetric matrix, the eigenvectors are orthogonal, right? The eigenvalues may be probably positive or negative. So if I want to try to store some p patterns, I want sine wy to be the same as y. And the largest number of patterns that you can store is going to be the maximum number of eigenvectors of w. And that is going to be n. specifically, if all of the patterns I'm trying to store are orthogonal, then I can simply design my W as saying y times lambda y transpose, where lambda are the eigenvalues. And if all of the eigenvalues are exactly 1, this gives you the Hebbian learning rule. So this is what the Hebbian weight matrix was. You took all of your patterns and you composed a weight matrix as y times lambda y transpose, where the eigenvalues were all 1. And the hope was that in the process, these guys are going to end up being the eigenvectors of your weight matrix. So any movement out of here is going to snap the network back to that same corner, right? What was the problem with that? Suppose I'm trying to store a smaller number of patterns than the dimensionality of the network itself, right? The number of bits in the network. Then I'm still composing a weight vector of matrix of this kind, where these R's are vectors which are not in the same subspace as the Y's. They are orthogonal to these guys, and their corresponding eigenvalues are 0. And so now that's all the Hebbian learning rule is doing. In all cases, for the patterns that you're trying to store, the eigenvalues are 1. So here's what happens. Consider the extreme case where you're trying to store n patterns. If I'm trying to store n patterns, then so p going from 1 to n. So these are n-bit patterns, and I'm trying to store n of these. These n patterns are going to span, they're going to represent all n eigenvectors of my weight matrix. So they're going to represent basically all, if I have, for instance, 3-dimensional space, I'm going to have one eigenvector for every dimension. And as a result, I'm going to have these eigenvectors together will span the space. And when they span the space, any random vector W can be written as a linear combination of these guys, of the patterns that I'm trying to store. When I transform Y with the matrix W, that's simply like saying the result is A1 times WY1 plus A2 times WY2 and so on. And since the eigenvalues are 1, WY1 is the same as Y1, WY2 is the same as Y2. So this whole thing simply returns to Y. So even though only these n patterns are the ones I was trying to store, for other patterns which can be expressed as linear combinations of these guys, any transform of those patterns is going to return the pattern. So basically all patterns are stable. This network remembers everything. It's a completely useless network. And if I'm trying to store fewer than n patterns, then I still have the same issue. If these are the patterns that I'm trying to store, y1 through yk, then any pattern that's entirely in the subspace spanned by these guys is also stable. And so that means it's not just these patterns that I'm remembering. I'm also remembering all linear combinations of these patterns. And if a pattern is partially in this subspace and partially in the R subspace, it doesn't matter. The moment I transform it the first time, it's going to fall into this subspace. And then wherever it falls, that point is going to end up being stable. So you have this issue with the whole Hebbian learning framework, in that Hebbian learning designs your weights matrix such that the patterns you're trying, such that it assumes that the patterns you're trying to learn are all random and orthogonal to one another. And then it constructs a weights matrix such that these patterns are the eigenvectors of W. And when they are the eigenvectors of W, all of them are given eigenvalue 1. And one consequence of this is that any bit pattern that's a linear combination of these guys ends up also being stable. And so this is why the whole Hebbian learning framework kind of fails. So, and of course, it gets more complex. What if the patterns are not orthogonal? What if the patterns are represented more than once? You can work out the arithmetic, but the basic flaw with the original Hopfield paper shows up when you actually begin looking at this behavior here, right? So let's sort of try to fix this, right? Let's deal with the whole business of trying to design the network as an optimization problem. And this is where it actually becomes real fun. All of the very fancy, complicated arithmetic that we saw so far becomes irrelevant when you make the problem, seemingly more complex. It actually ends up becoming more simple. So here is the energy that you're trying to of the network for any pattern y, right? So when you design the network, this energy must be minimum for the patterns that you're trying to remember. It must be high for all other patterns, because basically, remember, you want this behavior, right? If this is your state, and if you're trying to remember these two patterns, then you want the energy to be minimum here. It can be anything here, and then again, you want it to be a local minimum out here. Right? So you want the energy to be minimum at these guys, and at all other locations, you want the energy to be higher. And you want that because, if you initialize the network over here, you want it to sort of evolve into this location, right? Let's see how we can do that. Here's what we want to do. I'm also going to include a bias now, just for completeness sake. You want to estimate the weights and the bias such that the energy of the network is minimum for the target patterns, it's maximum for all other patterns. Okay. So here's what we will do. I will explicitly define my energy this way, and I'll say, find me the weights such that the energy of the network for my target patterns is minimized. Now, this is not enough, right? Simply minimizing the energy for the target patterns is not enough, because I may just end up making all the weights 0. So the energy is going to be minimum for my target patterns, but it's also going to be minimum for the other patterns. So I want to make this minimum, but I want to make the energy at all of these other locations high. So I will simultaneously say, minimize the energy at my target patterns and maximize the energy at all of the non-target patterns simultaneously. And this E, of course, is a nice quadratic term. So this becomes a very simple quadratic minimization problem. It's actually an integer programming problem because the y's are all bit patterns. But this is a very simple convex optimization problem. And so this is what we're going to do. We're going to minimize the W. We're going to learn the W such that the total energy for all of the target patterns is minimized, and the total energy for all the non-target patterns is maximized. Okay. So we are solving the problem. Here is my energy. This is my objective over here. If I want to perform gradient descent, all I will do is to take the derivative of my objective and use the simple gradient descent rule to learn my objective. I'm trying to minimize this with respect to W. So I'm going to say W equals W plus eta times the derivative of my objective term, where this E is simply this quadratic, right? So the derivative, my objective term is the sum of the energies of the target patterns minus the sum of the energies of the non-target patterns. The derivative of E of Y with respect to W is simply going to be YY transpose, or it's going to be actually minus YY transpose this. So that's why this becomes a plus. And so you end up with W equals W plus eta times the sum of the outer products of the patterns you're trying to store for all of the patterns you want to remember, minus the sum of the outer products of Y for all of the patterns that you don't want to store. And this will give you a simple iterative algorithm to learn the weights that should give you a weight matrix such that your Hopfield networks remembers the patterns you want to store and doesn't remember the ones that you don't want to store. Okay. So you can modify this a little bit. First, if anybody is still here, what would the issue be with this one? Are there any issues that you see? Guys? At this point, it seems like I'm actually speaking to an empty class. So anyway, yeah.
I think there are 11 people, but
yeah,
maybe we don't have any comment.
Yeah, I know. So what is the problem going to be over here? Anyone?
It may not descend to an optimum that we want.
Here's the bigger problem. Look at the term to the right?
It's the same.
If I've got like a 100-bit pattern and I want to store 50 of these guys, how many patterns do I not want to remember?
50, and they'll cancel out.
This is going to be 2 raised to 100 minus 50, right? The second term. These are all the patterns I don't want to remember. So for example, if I've got a 4-bit pattern, and let's say I want to remember 1, 1, minus 1, minus 1, and minus 1, 1, minus 1, minus 1. So these two, this one is going to sum over the two patterns that I'm trying to remember. And then here are all the patterns I don't want to remember. Zeros, 1, 1, 1, 1, 1, 1, 1, minus 1, 1, 1, minus 1, 1, 1, minus 1, 1, 1, 1, minus 1, 1, minus 1. So you see, there are going to be 2 of these guys I want to remember, and there are going to be 6 of these guys that I don't want to remember. Again, I'm saying 2 and 6 because it's symmetric, okay? And if I have n bits here, if I'm trying to remember k patterns, I'm going to require 2 raised to n minus k patterns that I don't remember. And this number is very, very large.
The maximization term dominates.
This second term ends up being, it's not just dominating, it's not going to be calculable. If I have a 1000-bit pattern, you're not going to spend your memory, spend your time computing this over every single pattern that you don't want to remember, right? So not only does it dominate, and it'll completely wash out what you have over here, it's also not going to be, you're not going to be able to calculate it. So, but before that, here are a couple of other things you can do. I can emphasize, not all patterns are equally important. So I can emphasize the importance of a pattern by repeating some patterns. So in this summation, I can present all of the patterns I want to remember, and the more important patterns could be presented more times, right? Here, I have to sum over all of the patterns, but do I really need to sum over all of the patterns? That is the question. And the answer is not necessarily, right? Now, look at this. For any given weight W, let's say I have an initial weight W, right? I'm trying to estimate the W. I have a current estimate. For the current estimate of W, I can plot the energy contour. If I plot the energy contour, I'm going to be something like this, right? And let's say these are the patterns I'm trying to remember. I want to adjust my W such that the energy at these patterns goes down, okay? The second term is trying to pull up the energy, adjust my W such that the energy at all of these guys goes up. Now, do I really need to spend a lot of time pulling up something out here, or can I just focus on the valleys, right? If I just focus on the valleys and I pull up the valleys while pulling down the energy at the target patterns, eventually you expect to end up with because at each iteration, you're just going to find the value and pull it up. So if there's any local minimum, which is not this guy, you're going to pull it up, right? So this means you don't necessarily need to go over all 2 raised to n patterns. You can just find the valleys and you can pull them up. And eventually all of these values are going to go over, become higher than your target patterns, and you're going to get an energy contour of the type that you want. Is this making sense, guys? Anyone?
Yeah.
So this is easy, right? The problem, what is the problem here? Anyone? Question is, how would you find the values, right?
Yeah. How
You're gonna have
long
to,
does it take it?
how do you identify the values for the current W? You just change one problem to a different problem. Why do you want to do that? So here's what I can do. I have an engineering solution. I can randomly initialize the network and let it evolve. And if I let it evolve, it's eventually going to stop at some point, and that's going to be a value, right? I can repeat this a few times, and each time it's going to find a value. So, and what is here? So here is my training. I'm going to initialize my W. I compute the outer product of all the target patterns that I want to remember, and more important patterns will be presented more frequently. I'm going to randomly initialize the network several times and let it evolve. It will settle at a valley. I'm going to compute the outer product of all of the valley patterns, and I'm going to use this equation here. I can average these guys better still to update my weights. Okay. Or if I'm doing a stochastic gradient descent version of it, where I'm going to be presenting one training sample at a time, then I would be sampling my target pattern in each iteration, then randomly initialize the network and let it settle at a valley. And I'm going to use this SGD version of this update rule to update my weights. Very simple. I mean, this is very pretty. It's so simple, right? Now, the problem here is, why do I need to randomly initialize? If you look at this, if I'm trying to say, remember this pattern, there's no point in my trying to pull up this valley. The valley that I'm most interested in is the valley that's right next to this guy, correct? So you want the memories to be stable. You don't care about this valley. You want these guys, these valleys. You want there to be no valleys next to the patterns that you're trying to remember, and far away from it, you don't really care, right? So here's what you will do. You can initialize the network at a valid memory and let it evolve. It'll settle in a valley. And if this valley it settles in is not the target pattern, you're going to raise it. So here's what you will do. You initialize your W. You compute the total outer product for all the target patterns. Again, more important patterns can be presented more frequently. Then you initialize the network with each target pattern and let it evolve. And it's going to settle at the nearest valley. And then you compute this term over here. This is computed over the target pattern. This is computed over the adjacent valleys. The difference is the gradient by which you're going to adjust your weight and you update your weights. Or if you're doing the SGD version of it, then you would do this one sample at a time. You sample a pattern, you let the network evolve. It's going to settle at the valley next to the pattern. You compute the difference between the outer product at the target pattern and the outer product at the valley, and use this difference to correct the weights. So, but you're still not done, right? Let's say if you're doing SGD in particular, this becomes a problem. Let's say you randomly sample this guy, but the network is already optimized for this pattern, which just happens to be the nearest valley, right? So if you started at this guy and let the network evolve, it's going to end up at this location where the network has learned to remember the pattern, and it's going to pull it up and it's going to destroy this memory, right? So you don't want this kind of behavior. So you come up with another solution. There's no need to really raise the entire surface or even every valley. What you're really interested in is that when you're drawing the energy contour, if you've got this, if this is your state, and if these are the memories you want to remember, then you want these guys to be in local valleys, and you don't really care what's happening out here, right? This is the width of the bowl within you, which you want your content addressable memory. So here's what you can do. You can decide what is the radius of the bowl within which you want the content addressable memory to work. And then you're going to raise the neighborhood of each target memory, just sufficient to make the memory a valley. And the broader the neighborhood you consider, the broader the valley, right? So starting from the target pattern, you're going to let the network evolve, but only for a few steps, maybe like 5 or 6 steps, or 4 steps, or even 1 step. And then it will stop. Maybe if you started from here, if you stop here, you're going to try to pull up the network just this location. So here is the SGD version. You would sample the pattern. So this guy, you get the outer product from the target pattern that you're trying to remember. Then you initialize the network at the target pattern and let it evolve for a small number of steps, 2 to 4. And you're going to end up at a down valley position, right? And you're going to try to pull up that down valley position down here. And so now your update rule is still the same as before, but you've simplified the problem even further. You'll be sampling target patterns. You let the network evolve a few steps. You get a down valley position. And the difference between the outer product of these two patterns is the correction you want to make to the network. And that's what you update the weights by. So is this making sense, guys? Yes, no, raise your hands. Well, at least some people did, right? And so this, once you begin thinking of it in terms of optimization, it actually becomes very simple. This whole Hopfield network business becomes very simple, right? You can store the network through optimization by minimizing the energy of target patterns while increasing the energy of neighboring patterns. So, and when you do this, it turns out you can actually store up to, theory says you can store up to order n memories. While, you get a lot of parasitic memories, but if you train this properly, those parasitic memories are going to be sufficiently far away that they won't really matter. So now you end up with this situation. The memory capacity of an n-bit network is, even with this optimization-based approach, the memory capacity is going to be a maximum of n. So how do I increase the capacity to store more than n patterns? That becomes an issue. And so here's how I can do this. I'm going to do something very simple. Let's say I'm trying to store n-bit patterns. Then the way we define the Hopfield network would have only n neurons, one for each bit. And an n neuron network could store at most n patterns, right? But then to increase the capacity, I'm going to augment these n bits by some k additional bits. I don't care what these bits are. I'm just going to take my, say I'm trying to remember 4-bit patterns, but I want to remember 40 of these. What I will do is to add, I want to remember all 16 of these for whatever reason. Well, not 16. Let's say I want to remember 6 of these, which is more than 4, right? I will take these 4-bit patterns and I'm going to add 20 don't care bits. And now, when I add 20 don't care bits, the new capacity of the network, if I've appended k bits to my original n bits, the new capacity is going to be n plus k. Although you're only interested in the first n bits. We're interested in n-bit patterns, but we augmented it with a whole bunch of bits that we're not interested in. And now when you compose the network is going to have a fully connected network over n plus k neurons, which you can think of as a fully connected network over k neurons, a second fully connected clique over n neurons, and the two are fully cross-connected, okay? So when I do this, I'm going to call these guys my visible neurons. These are the bits that I'm interested in. These are the don't care bits that I appended to my visible bits. These neurons I'm going to call my hidden neurons, right? And they can be set to anything to store a visible pattern. So to give you a more visual idea, let's say this is my n, and I'm trying to store bit patterns of this kind. The black represents 0, yellow represents 1. So this is a bit pattern that I'm trying to remember, right? If I have only n neurons, I can remember at most n such patterns, even using the optimization approach. So what I will do is to stick over here an additional k neurons of this kind to the pattern that I'm trying to remember. I don't really care what these bits are. The only purpose these bits are serving is to increase the size of my network so that now I can store n plus k patterns as opposed to just n patterns. These are what I will call don't care bits. So these guys I will call the visible bits. The don't care bits I'm going to call the hidden bits. And now the question really becomes, okay, I'm trying to store this n bit pattern. What is the pattern I put into these don't care bits before I design my network to store it? And there are different solutions. You can just fill them randomly by flipping a coin. Or for each visible pattern that you're trying to store, you can actually create multiple extended patterns and store them all. And then you can just store the whole thing using a standard optimization framework. So I'll sort of pick up in the next class from this point. With some luck, we should be able to get through all of Boltzmann machines starting from this point in the next class. And if this will be on Friday. On Friday, I may actually go the entire 80 minutes just so that I can wrap up this subject and switch to other. So any questions, guys? Stop the recording.